So remember that in nuclear equations, we're mainly interested in the nucleus and less about the electron cloud. Now, the law of conservation of mass and energy applies to nuclear equations, because what happens with nuclear chemistry is we can see that mass is is converted into energy. And so we don't always see conservation of mass, because sometimes it changes form into energy. But we can still make sure that everything is being accounted for by ensuring that the sum of the mass numbers are equal on both sides of the equation, and that is also true for the atomic numbers. And I want to remind you of some vocabulary here. Reactants are what go into a reaction, and the products are what come out. So let me show you the 5 most common types that you're going to learn in high school chemistry. So first we have alpha decay, which is where a nucleus breaks apart and a helium nucleus consisting of 2 protons and 2 neutrons leaves. Then we have beta decay, or called beta minus decay sometimes as well. That is where a neutron splits into a proton and an electron. The electron leaves and the proton stays behind. So because of that, you see no change in the mass number, but you do see a change in the atomic number. In gamma decay, you only lose energy, you don't lose any particles. And so you see no change in the mass number or the atomic number. But again, there is that loss of energy. Beta plus decay is where you lose a positron. A positron is the opposite of an electron. So just to show you here, with a beta minus, you have that neutron converting into a proton, electron, the electron leaves. With beta positive decay, you have a proton that converts into a neutron and a positron, and the positron leaves. Now, I told you they're opposites of each other. So with beta positive decay, what happens is that electron leaves the nucleus. It encounters an electron in the electron cloud, usually pretty quickly. And then those two things annihilate each other because they are antimatter. Okay, so coming back to my list here, so that's a positron. And then finally, we have electron capture, which is where an electron is captured into the nucleus from the electron cloud. And then you see the result of that. All right, so I'm going to show you 3 examples here where we're going to classify the reactions and we're going to finish the missing particles. So these are the 3 we're going to go through. If you want to try them on your own, feel free to pause now. Okay, so as a reminder, mass numbers and atomic numbers must sum to be the same thing on both sides. So here we have 238, and over here we have 4. So 4 plus what would equal 238? And the answer to that is 234. 92 is equal to 2 plus what? And the answer there is 90. So then we look at the periodic table to identify this atom. So element number 90 is thorium, therefore that is your missing particle. Then to classify this reaction, we would look at the particle. So the particle is 4,2 and as a reminder, that is your alpha particle, as you can see right there. Looking at the next one, we have the particle on the reactant side, which should be a big clue to you that this is electron capture, because that is the only type of radioactive decay that we talk about in high school that has the thing as the reactants usually. So sometimes you talk about neutron capture, but anyway, we won't worry about that right now. So we have 8337 rubidium. So 83 plus 0 is 83. 37 plus -1 is 36. 36 is krypton, and we already said this is electron capture. Okay, finally, so we have 4019K yields 4020 calcium. Here you're looking for the particle. So 40 and 40, so that's going to be 0 on top. 19 and 20. So 20 plus -1 will give you 19. And if your -1 is on the bottom, that makes it an electron, and that makes this beta minus decay.